Hi, welcome to the next lecture in the NPTEL series on Haskell. In this lecture, we will look at yet another data structure implemented as a module, namely queues. So, what is the difference between a queue and a stack, which we saw earlier? In a stack, elements are pushed and popped at the top. In a queue, elements join at the rear of the queue and exit at the front of the queue, just like any real world queue you see. So, here is we have already seen modules, so you can actually create a queue module and save it in queue.hs, and it is essentially this: elements have to be added at the end, which means that to add in a stack, to do a push in a stack, you did push x of stack x's is stack of x colon x's. Now you will do x's plus plus singleton x, right? Put x at the end of the stack, end of the queue. That is the only difference. Everything else is the same, right? So if you know how to create all this, and once again let us note that when you export, this is the module name and you are exporting the type constructor, but not the value constructor. Okay, fine. So now as usual, right? So fine, but what is the difference between a stack and a queue? In a stack it was efficient, in a queue it is inefficient, because you are doing plus plus. Plus plus is inefficient. It is not constant time, it is not really inefficient. You have to pay as much time as is the length of the list x's. Okay, so what do we do now? So each enqueue on a queue of length n takes order n time. Okay, and enqueuing and dequeuing n elements might take order n squared time, because you might keep on enqueuing some n by 2 elements, and then each time, so you may keep on enqueuing, and if you enqueue n elements, you have to already the time is order n squared, because it's n into n plus 1 by 2, right? And even if you enqueue and dequeue, it might not be really perfect, like you enqueue and you immediately dequeue, etc., so that the length of the queue is always some small. Okay, your length of the queue could grow unbounded, but within n. So in principle, it might take order n squared time. How do we make this better is the question. So we can actually make this better by, rather than thinking of a queue as this is the queue, this is the rear, this is the front head, let us say. You can instead think of it as this. Think of breaking the queue in two. Okay. So now what does it mean to add an element to the queue? You add it here. What does it mean to remove an element from the queue? You remove it from here. Okay, so both of these are lists, or you can think of both of them as stacks. Right? We know that adding and removing elements in a stack is efficient. So if you think of a queue as two stacks like this, then you can add in one stack and you can remove from another stack, and there will be a problem exactly in a situation where you keep on removing elements from this stack and this becomes empty, but there are elements in the other stack. What do you need to do? You need to borrow elements from that stack. But when you borrow, remember that you need to view the queue as this. This is one stack and that's one stack. Okay. If you want to borrow elements, you have to actually put all elements from here to there in this order, right? You have to sort of reverse the order, but it's okay. You can actually do reverse. Okay. When front wants to borrow from back, reverse back into front. Okay, that is the point. Okay, so one hopes that you will have to do this, but reverse also takes order and time, remember. So the hope is that you will only occasionally do this reverse, and every time you do the reverse, it will be the time you took there is compensated for by doing enough other operations at very low cost. Okay. Should be compensated for by doing many low cost operations. Okay, this is the hope, and let's see how we can actually achieve this. You want to maintain the invariant that Q is actually front plus reverse of back. As I showed you in the picture, this is front, that is the head of front, and this is the tail. So think of front as growing this way and back is also growing this way, but you want the Q to be this way. I am putting an arrow pointing towards the head, and the Q itself should be thought of as this, right? This is the Q. The arrow is pointing towards the head of the Q. So really Q is this is the front portion of the Q plus the back thing is actually this is the front of the back, etc. But you have to think of it in reverse. The head of back should be the last element. So you should think of it as front plus reverse of back. Okay, good. So that is the invariant that you want to maintain. To NQ, you need to add an element at the back. So and this is actually derived, right? Because you're saying Q is front plus reverse of back. So NQ of X in Q is nothing but Q plus X, but Q is reverse front plus reverse of back, remember. But plus is associative, right? It doesn't matter whether you did, I mean, it matters for complexity, but for correctness, it doesn't matter whether you concatenated these two lists first and then the third, or the second and third list first and then put the first list in front. So this is the same thing as front plus reverse of back plus singleton X. Oh, but this is nothing but the definition of reverse of X followed by back, right? So therefore, if you think of Q as so you can actually when you are representing Q as front and back, you will actually be doing something like this: NQ of front comma back equals front comma NQ of X in front comma back is nothing but front comma X colon back. Okay. To DQ, you have to remove an element from the front, and that calculation is much simpler. So except when front is empty. Okay. What if front is empty? Then you have to reverse back into front and DQ, right? And reversing, suppose once again, let's do calculation. Q equals front plus reverse of back. This is the invariant we are maintaining. What if front is empty? Then Q is so empty plus reverse of back is nothing but the same as reverse of back plus empty, right? So you can take this to be the new front and that to be the new back. Okay, so this is the idea. So at any point of time when front becomes empty, you can reverse the entirety of back into front, okay, and then you try to do the same DQ. So the code now becomes this, okay. So now, so here you have this is the constructor, type constructor, this is the module name, and here is a smart constructor. And you also have, you want to hide internal this thing, so I won't ever display a list, a queue directly, I am converting to list, conversion to list. Okay, good. So now how do I do this? So now my constructor, now I cannot use new type, cannot use new type. Why? Because the value constructor, single value constructor, but it has two arguments. If instead you used this is possible, because now there is, it's one argument which happens to be a pair, that's okay. Okay, now you can do new type, but if there are two explicit arguments like here, then you cannot use new type. Okay, fine. So I want to show, so if A is showable, then Q of A is also showable, and what I say is that show is nothing but convert the Q to list and then show it. Okay, from list, how do I convert from list to Q? I just put the list as the front and take empty to be the back. To list is F plus plus reverse of B. Okay, a Q is the front plus the reverse of the back, right? So I can do all this. Now I need to implement NQ and DQ. NQ is simple. NQ of X and Q of B is nothing but Q of F and X colon B, as I told you earlier. DQ is where you have to pay a little attention. If both front and back are empty, then you are trying to DQ from the empty Q. So you will print an error saying empty Q. If back is non-empty, DQ of Q empty list B where back is non-empty, then you will say it is X, X is the DQ'd element, and then QF empty list where the reverse of B is X colon F. Okay, so you reversed B and it had a first element, and so essentially if you want to think of it as back, this is back looking that way, but this is F and that is X. Okay, so back is reverse of X, F and X, or in other words, reverse of back is X followed by F. So then you just move that F to front. Okay, so you have Q F empty. Okay, and in general, if my front itself is non-empty, then there is nothing much to do. X colon F is the front earlier, now the front is F. Okay, so this is it. So now and if I want to create an empty Q, I will do Q empty empty. Is empty of QFB is null of F and null of B. Okay, this is a very efficient queue. Why is it efficient? Okay, so that requires some discussion, and this leads us to something called amortized analysis. And amortization is an accounting term. It means averaging or spreading out. I don't know exactly how they use it in accounting, but maybe if you bought something and whatever, so if you lose something or whatever, you will spread it over across many years so that you can calculate tax accordingly. I suppose one has to check it up. But here, what we mean by amortization is that you distribute the reverse that you occasionally do spread its cost across all operations. In accounting also, if amortization makes sense only if you are talking about some extended period where you can spread some gain or loss or whatever over that period. Similarly, in computer science also, in data structures, amortization makes sense only when you consider a data structure and a sequence of operations being performed on the data structure, not a one-off operation. Okay. Suppose you take a queue and add n elements to the queue. So, you start from queue empty and you keep on adding elements to the rear. So, you would have a queue like this. Okay. You originally added qn, then you added you originally added q1, then you added q2, etc., etc. This is the order. Q1 qn is the order of joining the queue. But qn is the order of storing in the back. In the back list. Okay. So, now suppose at this point you want to do a DQ. It takes order n time to reverse the list, right. Now, it seems that after one DQ you get Q2 dot Qn empty list. Now, it seems like if I perform n operations, what is the worst case time that each operation can take? Order n. So, it seems that I can n operations will take order n square time, but the point is once you have done a reverse, you do not need to worry about reverse of a length n list. You do not need to worry about the next n minus 1 DQs. Okay. But what if there aren't n minus 1 further DQs? Here is another way to think about this. Each time you add an, so why did your DQ take order n time to reverse the list? Because you actually add n queued n elements, right. So, what you do is upfront you pay all this cost. So, let us say NQ takes 5 steps internally. So, you account it as 10 steps for each NQ. Now, if I do n NQs, I will take in my accounting for 10 NQs, for n NQs, actual time taken 5n, my accounting is 10n. So, what is surplus? 5n, and I use the surplus to pay for this reverse. Let us say reverse takes 5n steps for length n list, let us say, right. Anticipating a later reverse, when I try to DQ, I will already keep putting some money in the hundi, let us say, so that later I can break the hundi open and use it. Okay, this is what is amortization. Okay, paying upfront, let us say, but for each operation I pay a small amount, but if I accumulate it for n operations, then I can use it for a later costly operation. This is amortization. It's a very nice idea, and you can use it to have a simple implementation of Q, which is also efficient. Okay, now yeah. So, you can actually do this amortized analysis in multiple ways. Here is another way. How many times is an element touched? Once when it is added to the second list, once when it is, twice when it is moved from the second to the first, once when it is removed from the first list. So, each element is touched almost 4 times. So, if you do n operations, you will take 4n times. Okay, that is one way of counting this. So, in the slides I have an application of this, which is a nice puzzle, but I'll try to upload these slides and you can take a look at it yourself, and I'll also try to upload the code, or in a later session we can go through it. But it's a very nice fun application of queues. But I'll stop with this now because these lectures have already become too long with data structures. Just the takeaway is that queues are a very fundamental data structure, and yeah, okay. So this is a nice puzzle, but I'll just upload it in the slides and you can take a look at it and enjoy it yourself. I'll also try to somehow upload the code for this so that you can take a look. Okay. Thank you very much.